The goal here is to prove that if I have any sequence that's bounded, any sequence of real numbers that's bounded, then if I divide the terms of that sequence term by n, then that resulting quotient gives me a sequence which converges. And then we're hypothesizing that not only will it converge, it will necessarily converge to 0. So this statement in red here is what we know about Sn. The statement in blue is what we want to show about Tn. And then we convinced ourselves, doing a little bit of scratch work, that this inequality that the t's, the sequence of t's, needs to satisfy is equivalent to an inequality on the sequence of Sn's. Namely, because Tn is Sn over n, and I multiply both sides of that inequality by n, the inequality that we really would like to establish is that the absolute value of Sn is less than epsilon times n. So this is now what we'd like to prove, because this is equivalent to that statement about the Tn's. And then the trick is that we know something about the Sn sequence that comes from the assumption that the Sn's are bounded. So we know that the Sn's are less than or equal to m in absolute value, and that that statement holds for all n. And then we need to show that there exists a capital N such that for all little n's past that capital N, that this inequality holds, that the Sn's are less than epsilon times n. So let me just quickly sort of look at a picture that might help to illuminate the logic of what's going on here. Saying that the Sn's are a bounded sequence means that between plus and minus m on the number line, every single term of my sequence Sn must live inside there. Right? Meanwhile, what do epsilon n look like? I'm just going to focus on the epsilon n for a second. Highlight that in. So thinking of this as a sequence, maybe let me put it that way. So let's call that sequence, let's call it mn, or something like that. Okay, so the sequence mn equals epsilon n. What does that sequence look like?
Linear.
Yeah, it's a linear progression. It's an arithmetic sequence whose common difference is epsilon. Okay. So when n equals 1, m sub 1 is going to equal epsilon. Right? And if epsilon's really small, that could be really close to 0, right? But then m sub 2 is going to be 2 epsilon. M sub 3 is going to be 3 epsilon. 4 epsilon, 5 epsilon, 6 epsilon, 7 epsilon, 8 epsilon, and so on and so on and so on. Now, if we had chosen, let's say, capital N equals 3, then will it be true that we can bound all of our Sn's to be less than epsilon times 3? Not necessarily, because 3 epsilon here in this picture is still in the middle of this interval. And so there could be some terms, some Sn's that are bigger than it. But what's eventually going to happen with the epsilon n sequence?
Reach m?
Yeah, it's going to reach m, and not only reach it, it's going to surpass it, right? Because m is not going anywhere. It's what we call a uniform bound on the Sn's, right? No matter what n we choose, Sn is less than or equal to m in absolute value. So m's not going anywhere, but the epsilon n's are marching forward in an arithmetic progression that's eventually going to overtake m. So at some point, epsilon n becomes bigger. I'll write it this way. Epsilon n becomes bigger than m, and we know that m is bigger than, or equal to, at least, all the absolute values of the Sn's, right? So that's the notion behind this proof, is that eventually this is going to happen. And as soon as that happens, for that value of n, and for all the n's past that, right? So let me say that. At some point, for all n greater than or equal to some capital N, and so in our picture, this is probably the capital N, epsilon times capital N. For all n's greater than or equal to that capital N, epsilon n is going to be bigger than m. And if it's bigger than m, that means it's also bigger than all the terms Sn in that sequence. So if that's the idea, let me hear from your group. What did you do to get started, or did you do any additional scratch work, I guess, in order to get you closer to this proof? So you're saying, if we want this statement right here to be true, in other words, if we want m to be less than epsilon n, then we want to choose n's which are bigger than m over epsilon. And so as long as my little n is bigger than m over epsilon, then this statement is going to be true. And because that statement is true, and we know this statement is true, then the absolute value of the SNs will be less than epsilon n. So now we can begin our proof. I'm going to write my proof in purple, magic purple. Go Northwestern Wildcats in the NCAA tournament for the first time in ever. Yay, alma mater. So in purple, how do we start this proof?
Let epsilon greater than 0.
Yes, every proof of a convergence begins with addressing this universal quantifier right here for all epsilon greater than 0. So we have to prove something which doesn't depend on the value of epsilon, so let's let epsilon be greater than 0 be arbitrarily chosen. Great. So someone chooses an epsilon for us. Now, we want to show that there exists a capital N, such that some stuff is true. So now is our time to be creative and crafty. So we need to choose a capital N such that all of my little n's that are bigger than that capital N will satisfy this inequality. So how should I choose my capital N? How did we do this before when we were proving that sequences converged?
Like the ceiling function.
Yeah, once we did all the scratch work to figure out what we wanted little n to be bigger than, right, then we just needed to take this number, which may or may not be an integer, and round it up to the next natural number, so that if that's our capital N, then having n be bigger than that capital N will guarantee that it's bigger than m over epsilon. So we'll take m over epsilon and just round it up with that ceiling function. Right? Okay, now here's a slight bit of a proof writing issue. It's really more of a proof reading issue than a proof writing issue. If I'm just reading this proof, at this point in the proof, I don't know what in the world m means. So we should tell the reader where we're getting this m from. Where are we getting the m from?
From our assumption.
From our assumption, right. So I'm going to bump this statement down, and we'll put in a sentence that tells us where that m comes from. So I might say something like, since Sn is bounded, there exists an m, a real number m, such that for all n, for all natural numbers n, the absolute value of Sn is less than or equal to m. I heard this group talking in slightly different language that also works here. You might say, let m be an upper bound for the terms of the sequence Sn. So that's kind of an alternative way to phrase this. Let m be an upper bound. And again, we call it a uniform upper bound because it's an upper bound on every single term of the sequence.
When you say it's a bounded sequence, does that mean it's bounded above and below?
Yes, if we say bounded without specifying which, it means that it's bounded from above and from below. And you'll notice that using the absolute value in this definition actually gives us both the upper and lower bound, m and minus m, respectively. Okay, so one way or another, we have to introduce our reader to m in our proof, and so we'll add that statement in red there. Say, let's let m be the real number which meets this definition, which we know to be true because we're assuming that the SNs are bounded. Then we can choose n equal to the ceiling of m over epsilon. Subsequent to which we'll now let little n be greater than or equal to n, again arbitrarily chosen for us because we get no control over that. Let n greater than or equal to n be arbitrarily chosen. A lot of proof writers aren't as verbose about the arbitrarily chosen part, but I think it's important while we're still in a mode of making sure that we're not skipping steps and we're not taking anything for granted. We don't get to choose little n. We did get to choose big N. Okay. So now how do we establish the last part of this claim, that for the little n that we chose, sorry, for the little n that was arbitrarily chosen for us, and for the epsilon that was arbitrarily chosen for us, that this inequality must be true. How do we prove that?
Substituted that in the equation.
Yeah. So we'll start with this inequality, Tn minus 0. And we'll substitute in what we know Tn to be. It's Sn over n. Right. And if I subtract 0, that's not really doing anything for me. And now we know, based on the fact that n is greater than or equal to capital N, we also know that it's greater than or equal to m over epsilon as well, right? And so there we can make our substitution. Maybe I'll do it in 2 steps. So since n is bigger than or equal to capital N, that means that if I replace little n by big N in the denominator, do I want a, let me finish writing this. Do I want, what kind of an inequality sign do I want here? Less than or equal to, right. If I replace the denominator by something larger, sorry, replace the denominator by something smaller, because capital N is smaller than little n. If I replace the denominator by something smaller, I get a fraction which is larger. So that gives me the less than or equal to. We'll code that in green just to stay consistent with what's above it there. Okay. But then what do we know about capital N? We know it's greater than m over epsilon. Greater than m over epsilon. And so if in the denominator I replace n by m over epsilon, then again I know that I have something which is less than. Right? Okay. But now we need to use something that we know about Sn. Namely, what do we know about Sn? Actually, it's here in our proof. Yeah, it's less than or equal to m. So one more time, we'll use an inequality estimate. I'm going to kind of write it off to the side here. Sn is less than or equal to m. And so therefore, this is, now since the Sn is in the numerator, let me move this over a little bit. Just want to make us some room. Since the Sn is in the numerator, if I put an m up there, m over epsilon, what am I going to get as my inequality symbol this time? Yeah, this m is greater than my Sn's, right? And so I want here a greater than or equal to. So replacing in the numerator gives us the same direction as the inequality, which lets us make the replacement. Okay, well, this is great, because now all I have to do is some algebra and simplify inside of the fraction. Dividing both numerator and denominator by m, I have the reciprocal of 1 over epsilon, and the reciprocal of 1 over epsilon is epsilon. I never got rid of the absolute value, but why can't I? Epsilon's positive, yeah. By assumption, epsilon is positive. And therefore, we have an epsilon right there where we want it. So when we read this argument from beginning to end, absolute value of Tn minus 0 is less than or equal to less than or equal to epsilon, which is what we wanted to prove. Thus, not only have we shown that the Tn's are convergent, we've shown that the limit as n approaches infinity of Tn is equal to 0. So the inverse of this statement is not true. And for the inverse, remember, we take the negation of both the hypothesis and the conclusion, and we turn them around. And now we want to show that this is not a true statement. And so we want to show that it's possible for there to be an unbounded sequence. And Matt, you just said that the sequence 1, 2, 3, 4, etc., Sn is equal to n. I think we can agree that that's not a bounded sequence. In fact, I think we proved that last class. So that's not a bounded sequence. But then Tn, Sn over n, what does the Tn sequence end up being? Tn sequence ends up being a constant sequence of ones. And how do we know that a constant sequence of ones is going to converge? Yeah, it converges to 1. We can show that for all epsilon greater than 0, there exists a capital N such that for all little n bigger than or equal to capital N, absolute value of Tn minus 1 in this case is less than epsilon. But since Tn is equal to 1 for all n, we can take, let's say, even just n equal to 1, making the entire sequence satisfy this inequality, and the entire sequence satisfies the inequality because Tn minus 1 in absolute value is 1 minus 1, which is 0.